Yeah, like last time when we talked about k-fold cross-validation for model evaluation, let's now take a look at some code examples for k-fold cross-validation, but now for model selection. So we will take a look at some code examples here. And yeah, the code is also on GitHub. I will also include the link on Piazza, on Canvas, so you can also download the code notebook and play around with that later. Okay, so here is my code notebook. Like usual, the watermark for checking the version numbers of our packages. And then yeah, first I'm starting with grid search. So for hyperparameter tuning and model selection, grid search is really useful, like I said. So we will take a look at a decision tree classifier on the iris example, and using then grid search from scikit-learn. Yeah, we are again using the iris example. I know it's not super exciting to talk about iris, but I think, yeah, really if we would introduce more complicated data sets, the lectures would take forever. So I think with iris we can keep it more simple, and soon we have your class projects. So in your class projects, I'm excited to see some new data sets, and also the other students will see some new applications in data sets, which will make that also interesting. Okay, so we first split our dataset into training and test sets using 15% for the training test set and 85% for the training set. It's like the usual stuff. And here we start now with grid search. We use two hyperparameter options. We use the max depth for decision trees, which we define as either 1, 2, 3, 4, 5, 6, or none, where none means there is no restriction on the maximum depth. And as criterion, we evaluate Gini and entropy. In practice, it makes little difference, but yeah, so that we have another hyperparameter to look at, we also include that one. And in grid search here, we are now giving it this parameter grid. Yeah, note, I don't think you have to have this list here, actually. So you can also just feed it the dictionary, but what you could do is you could feed it two dictionaries like this. So you can have two dictionaries, and you can have you can say, for example, I only want to explore the max depth with Gini for like this, only with, let's say, Gini or something like that. You can hard code this, and then for the other one, for entropy, you can say you want to explore all of these settings. So this would be one option. Let me see if that actually runs. No, so yeah, this would actually work. So you can specify different scenarios, and this can be useful if you have conflicting parameters choices. So for example, if you have some conflict between, let's say, running Gini with a setting of 5 or something like that. In this case, there is no conflict, so you don't have to worry about it. But in some cases, there may be a conflict. For example, if you have a kernel support vector machine, a kernel support vector machine has a gamma parameter, but it only exists if you have a nonlinear kernel, for example. Does it actually? Yeah. So in that way, you can specify that the gamma parameter is only tuned if you use a nonlinear SVM, but if you also consider a linear kernel as a hyperparameter, for that one you would not tune gamma because there is no gamma. Things like that. Anyways, but let's go back to our simple case where we only have one hyperparameter grid. Like I said, you don't need the list outside, then you can just give it a dictionary. Yeah, so what we define is the parameter grid. And then we set refit to true, but this is also the default setting, so you don't have to specify this explicitly. You could technically get rid of this line. It would get the same effect. It would only have an effect if you set it to false. Anyways, so let's leave it explicitly, so then it's more clear for reading what's going on. Let me make this a little bit bigger. So then we set CV to 10. CV here means k-fold cross-validation, so you can set an integer. So this is for k-fold cross-validation. If we have a classifier here, this will be stratified. So this will be stratified k-fold cross-validation. Stratified k-fold cross-validation, like you remember from last time, means that the proportions of labels will be kept constant in the loops, in the folds. Then also, if this is a classifier, it will use accuracy as a metric for deciding what the best hyperparameter setting is. So it will use classification accuracy. If this is a regressor, I think scikit-learn will use the R2 score, the coefficient of determination. You can also set n jobs, like for running this in parallel. Like I mentioned several times before, it can be problematic on certain Windows computers, not on all Windows computers, but at least on some, to use multiprocessing in Python. There's some I don't know, weird bug in some versions of Python. I don't know the details. If you're on a Mac or Linux computer, this should almost never cause any problems. So you can set it to -1 to run multiple evaluations in parallel. But if you have problems with that, you can set it to none. So once you have specified all of that, you can then fit grid search. So you can then do the fitting. And yeah, so let's actually run that. So we find that Guinea with a max depth of 3 performs best, and the best accuracy is 96%. So this is the average accuracy on the test folds. So if I go back to my lecture notes here, this refers to the performance of the best model here. So for example, it could be, if let's say this is max depth 3 with Guinea, then this performance here, that's the average over the test folds. That's what this refers to. Yeah, we can get it by best score. So remember, the underscore parameters are the ones that are only available after model fitting in scikit-learn. So this would be a case where we can, after fitting the grid search here, after that we can get this best score. So the score would be, in case of a classifier, it would be the accuracy, the average accuracy over these validation folds. And then with this attribute we can get the corresponding parameters. For example, in this case it's Guinea with max depth 3. So it selected this combination here as the best model. However, if you're interested in more details, you can manually inspect the results. So all the results are stored in a dictionary. So it's actually a big dictionary, so it's kind of tedious to look at it like this. So but you have all the data if you want to take a look at it. So I only select here the mean test score. So the mean test score refers to the average over these validation folds. So they call it test folds, which is why it's not validation score but test score. Yeah, so I'm iterating over these for each hyperparameter setting, and then I'm printing the score together with a parameter setting. So if I do that, you can see then the score, the accuracy for each hyperparameter setting. So Guinea with a max depth 1 only gets 65% accuracy, which is kind of expected because this is just a decision tree stump. So here low performance. And yeah, you can see here between those two there's actually a tie. So they get the same performance. Actually, all these get the same performance. And this one you can see is only slightly above. So this one is only slightly above these other ones. So it selected this one because it's slightly better. But you can see for the entropy, it gets actually the same performance. So entropy or Guinea, it doesn't really matter whether you use one or the other. The reason why Guinea was selected is because it's first in this list here. So in scikit-learn, it's usually, if there's a tie, it would always select the first item in the list. Okay, so yeah, we can also optionally summarize these results in a heat map if we want to. So that's being done here. So here I just wrote some simple code using my heat map function in mlextend and just summarize the results in the heat map. I don't know why this is so hard to read. Usually I have a function that it would make the font white if the background is dark, but somehow it doesn't work here. I have to take a look at that. But yeah, this is a heat map summary. You can see that whether we use Guinea or entropy has almost no effect. You can see it's a little affected here in this range. You can see for entropy the performance is a little bit lower compared to Guinea, but the best performance is still the same. So Gini or entropy does not really matter whether we use one or the other in practice. Yeah, so after running grid search, we would fit a model with the best settings on the whole training set. So this would, if I go back one more time, this would correspond to this step 3 here. So we would then fit the best model on the whole training set, because like I said, in each round we have multiple models. If we have 10-fold cross-validation, we would have 10 models here. In this figure, it looks like we used 5-fold cross-validation, so we would have 5 models. So which one would we then select? Yeah, we would then do step 3. But in practice, we actually don't have to do that, because grid search does it already for us, unless we set refit.false. So this refit.true, it will already automatically carry out step 3 here, so we don't have to do it ourselves. And the best model will be available. The best model will be available via the attribute best estimator. So if I go here, you can see this is actually a decision tree classifier with max depth 3. Gini is not written here, I think because it's a default parameter. Let me double check criterion. So if we check for criterion, it should give us Gini. Yeah. Okay, so yeah, so this is already our best model. Best hyperparameter settings fit to the whole training set. So we can go ahead now, and if I go back here, we can now do step 4. So we can do step 4, and then we see it has 95.65% accuracy on the test set. We could do step 5 optionally, just fitting it to the whole data set. We are not doing it here now. It's another optional step we could do. Okay, maybe you are interested in that. We can also do the grid search CV with the out of back bootstrap iterator. We defined, where are we now? Sorry, here. We can also do it with the out of back bootstrap estimator that we defined in the previous lecture. So we can use this bootstrap out of back object that is similar to k-fold or stratified k-fold, as we talked about in an earlier video. And we can also plug that into grid search if you wanted to. So you can do the cross-validation based on the bootstrap method. So you can do that. And then you can also, if you are interested in that, you can compute the confidence intervals. So here actually it turns out this is the same performance as we got here in the test set, which is actually a good estimate of the performance. And the confidence interval would be between 89% and 100% using this percentile method that we talked about. So here it's just briefly how we can also do grid search not only with k-fold cross-validation but also using the bootstrap method. Okay, another point to consider is what happens if we have to do feature scaling. I mentioned in the lectures when we talked about standardization or min-max scaling that we have to use the training set parameters to transform the test set. The same is true when we do the k-fold cross-validation. So for k-fold cross-validation, if I go back here, we would also derive for each round the values, let's say in standardization, the mean and the standard deviation from the training folds, and then use those to also transform the validation fold. So how can we do that concept with scikit-learn and grid search? Actually, scikit-learn will already take care of it for us if we use pipelines. So it's already implementing these best practices. So we can use the pipeline that we talked about many lectures ago now. I think it was before the ensemble lectures even. So we can define a pipeline, and if we want to include scaling, which does matter for k-nearest neighbors, not for decision trees, but for k-nearest neighbors and many other classifiers. So we would then define our pipeline, including the standard scaler, and then here the k-nearest neighbor classifier. And then we can tune the values for the number of neighbors. We can have multiple hyperparameter settings. Here I'm just considering the number of neighbors as one setting, and then P, that's the Minkowski distance, as a second setting. So 1 would be the Manhattan distance and 2 would be the Euclidean distance. And then I can use this pipeline as an estimator in grid search, use my parameter grid, define the number of jobs, and here I'm using Bootstrap out of bag, but you can also just use 10 for k-fold cross-validation, and then run this. So we can also actually replace it by 10 if you wanted to. Anyway, so here the interesting part is that using the pipeline will take care of it for us, of deriving the parameters from the training folds and applying them to the test folds. But then notice how you have to specify the hyperparameter names. So here you have to prepend the name of the object that you want to use the parameters for. So we don't do any tuning for the standard scalar, only for the k-nearest neighbor classifier here, but it may be if you use principal component analysis here that you have to specify also some parameters for principal component analysis. So here this name comes from the fact it's just the name of the object in all lowercase, and then the number of neighbors and the P. So okay, let's run that. I can actually also simplify. Okay, it was fast enough. Otherwise, I would just simplify this. I can maybe do. Oh, I can see it's actually quite overfitting here to the test set. Let's do none. So for those who can't do multiprocessing, and then we set it to 10. That's also overfitting. But yeah, so here it's just an example of how we can use grid search together with the pipeline where we have feature scaling and k-nearest neighbors. Maybe spontaneously let me try to use principal component analysis so you can see how we can tune two parameters. Is it PCA? Yeah. So we can use, let's say, PCA here, and this should have an n components, I think. Yeah, n components. So we could then also consider so we have to do PCA. Oops, yeah, actually where I put it doesn't matter, I can put it between. I think it's easier to read if I put it as first item. PCA n components, and then we can just say 1, 2, 3, or 4. 4 doesn't really matter, make sense, but yeah, because we have 4 features in the data set. Okay, so yeah, we can also do that. So it will then, okay, it found that 3 components is best and 5 neighbors. Performance didn't really improve, but yeah, that would be how you would incorporate multiple objects for which you want to tune hyperparameters. Now, lastly, the randomized search. So here, in contrast to setting a grid, we sample from a distribution, which is either discrete or continuous. And instead of running all the combinations exhaustively, we have an n-iter parameter which runs a specific number of iterations. So it's deriving a specific number of random samples from the distributions. To understand how that works with the random distributions, let's take a look at the param sampler, which is used in randomized search under the hood. So this is just not running any tuning, it's only giving us parameters. So for example, consider a case where we have this parameter grid of parameter 1 and parameter 2. For parameter 1 I have possible values 1, 2, 3, and for parameter 2 I have A and B. And here we are only running 10 iterations. Notice there are only 6 parameter combinations, right? But we set it to 10. So in this case, it will only give us the 6 possible ones, because these are not probability distributions, these are lists. So in case I have randomized search and I specify lists, it will behave similar to grid search, because it will use the number of combinations that exist. So in that case, when we use lists, randomized search would be the same, except that these would be evaluated in a random order, which can sometimes be also beneficial if you want to stop it early, for example. Okay, so here's the more interesting case now, where we actually use a distribution. Here I use a uniform distribution. This is, I think, a discrete distribution, random integer. And so if I set it to low 1 to high 4, the upper boundary is not included, so it's a half-closed, half-open interval, half-closed. So it will only consider the integers between 1 and 3. And here now it will evaluate more cases, all 10, even though there are technically only 6 combinations. This is now a distribution, so we'll just keep going. If I set it to 100, it will just keep going. There will be repetitions, some of them will be identical, but that's the default behavior. So now it will randomly select an integer between 1 and 1, 2, or 3, and then combining it with a and b. So you can see so these are actually identical, you can see that. So it will just choose a random integer and then pick either a and b. So that's how it works. So for such simple cases, it's of course not useful to do that, but in practice there are cases where we have continuous distributions. So we can, for example, use the uniform distribution, which gives us a value between 0 and 3. So here is just a random sample 1000 times to show you how it looks like. Of course, it's a random distribution, small number, so it doesn't look perfect. So we can also give that to our parameter sampler here, and then it will draw random numbers from this distribution. Okay, so here I have an example using randomized search for our HIST gradient boosting classifier, and the HIST gradient boosting classifier has a learning rate. And for the learning rate, it may make sense to look at exponential values. It depends on what hyperparameter you consider, but for example, let's say we are more interested, we know we have some prior knowledge, or it's just we just think there's a more useful value between 0 and 1. That's where we want to spend most of our time. And looking at values over 1 is maybe not as worthwhile. So I set, or I use the exponential distribution here with a scale of 0.4. I think this location is 0, and then just to visualize it, I've drawn 10,000 samples, but here we just give it this distribution. I'm also giving it a random uniform distribution, a discrete one, for the integer for the maximum depth of the decision trees, set between 3 and 10. Also a regularization parameter. Here I'm using a uniform distributions for values between 0 and 1. And so this would be my hyperparameter grid. I use just 3 distributions, and then I'm using it similar to Grid Search CV. So you notice this is very similar to Grid Search CV. I have an estimator, I have my parameter grid, I have CV, which is k-fold cross-validation, stratified k-fold cross-validation if this is a classifier. There's also the refit, and there's also the n jobs. What's new is the random state. It's just in which, for sampling these values from the distributions and in which order. And what's also new is the number of iterations. So here I'm looking at 200 candidates. So I can run this now. I should import this first, of course. Okay. So and then this is running, might take a while. This is running 200 iterations now. Okay, I don't know exactly how long that would take. Hopefully not too long, but it's also not that important that it finishes before I finish the video, because I was just showing you how randomized search works. And randomized search is essentially, the API is very similar to grid search, except now that we have the number of iterations, we can use distributions, and we have the random state. All right, here it finished. So it gets a 97% accuracy, and it found 0.77 is a good regularization strength. Learning rate is very small, 0.01. The maximum depth is 5 here. That would be a good setting for our case. Okay, yeah, so this was grid search and randomized search. And in the next video, what are we going to cover? We are going to cover the one standard error method. It goes back to the concept of the law of parsimony. So how we also consider another criterion for selecting our hyperparameters instead of just performance, also looking for simplicity. But we will talk more about that in the next video. All right.